I will instruct you how to complete the parallel combination of capacitor lab. So here are few pre-lab questions you must answer before going into the data collection. So for example, what is the formula for a parallel plate capacitor? You have to answer in terms of the geometry of the capacitor. For example, a capacitance of a parallel plate capacitor depends upon the area and the distance. Okay, so you have to write down and you can find all the answer from the lecture videos. What is the formula for the equivalent capacitance or net capacitance if they are connected in parallel combination? If the capacitors are connected in parallel combination, the net capacitance is always an algebraic sum of or a scalar addition of all individual capacitor. So you have to write down all the answers here. So now I will simply go to, again, as I said, you can find out all the answer from the lecture videos. So now let's complete this table here. So you have to connect two capacitors in parallel. So for this data taking, all you have to do is go to the fit simulation here. Let me go here, the two in parallel. Reset, I'm going to reset everything so you can follow. So to type in, so if you type in, how did I get in here? So if I simply type in the fit capacitor, you'll get it here. All right. And then once you do that, go to the multiple capacitor and click on two in parallel. Okay. Then the third thing you have to do is you have to fix all the capacitor to 3. When I say 3, that means it is 3 times 10 to the negative 13. That's what it means. 3 times 10 to the negative 13. So then simply go to 3. And then you can vary this one. So the smallest number is 1. So let's do that. And then here it is asking you to calculate the net capacitance from simulation. So in order to read the simulation number here, that what it is here, 0.4 times, you see here 0.4 times 10 to the negative 12, that means it is 4 times 10 to the negative 13. So simply come here and write down 4. And then using the formula would be simply equal to 3 plus 1, that is 4. And the total charge from simulation. So what you can do here, the total charge, so come here, the stored charge, and of course you have to apply the 1.5 voltage here. The total charge is 6 times 10 to the negative 13. Okay, 6 times 10 to the negative 13. If it is out of range, then you can just use this zoom button here, zoom in and zoom out. 6 times 10 to the negative 13. So that's the from the simulation. And the next question will be, how do we calculate from the formula or from the equation? So I will answer these things just in 1 minute. First, let's calculate the potential difference, V1 and V2. So V1 and V2, so you take a voltmeter and then place against the capacitor C1 and read the reading, that is 1.5 volt. Come over here and you have to write down 1.5 volt. And exactly the same way, take it to the C2 and then it is saying 1.5 volt and 1.5 volt, and make sure that all the readings are in red color. And then what's the remarks here is the V1 and the V2 are both equal, and the reason is both capacitors are connected in parallel combination. Now I'll show you how to calculate from the total charge from equation, but we'll calculate Q1 first. How do we calculate Q1, or the charge on capacitor 1? The simulation does not let you to calculate the charges on individual capacitor. It doesn't let you. So the way you calculate using the formula is here. Q1 is C1 times V1. That's the formula. C1 times V1. The C1 If I go to the table here, C1 is 3 and V1 is 1.5. So I need to multiply these two numbers together and the number I will get is 4.5. The next thing, in order to calculate for the Q2, so look at the Q2 here. Q2 is C2 times V2. So I have to multiply this number 1 times V2. So, and the number I will get is 1.5. Sorry. So just 1 second here. This one will be Q2 is 1.5 and this is Q1 is 4.5. And the total charge, this is the total charge from the equation, and it has to be added together 4.5 and 1.5, and this number is 6. And you see all this, the total charge from simulation and the total charge from equation is exactly equal. So that makes perfectly sense. So our calculation is correct. Okay. So now exactly the same way you can fill all all the other data. So now let's go back to the other question here. So now you have the three capacitors connected in parallel, and this is 3 and this is 1. So let's do here. So three capacitors in parallel. So I have to make this one 3 and 1, and you see this is fixed at 3, C2 is fixed at 1, and then all you have to do is change C3. C3 goes from 1. So when it is 1, so let's calculate. You see this is 3, 1 and 1. So what is the net capacitance? The net capacitance you read here is 5 times 10 to the negative 13. So come here and you have to write down 5 here. So that's the 5. And then from formula, how do you calculate from the formula? The formula tells you that all the capacitors has to be added. C1 plus C2 plus C3. So that means if I add all these numbers together, 3 plus 1, 4 plus 1, 5. That's the 5. And that makes perfectly sense because both capacitors using the simulation and for the formula gives you exactly the same number. Okay, and I'll come to this one later, the charge. Let's do the potential difference here. Potential difference here. So I will make it a different color here. Okay, I'll just make it, for now I'll just make it a different color here. All right, so V1, V2 and V3 potential difference. Again, what you have to do, you just take the voltmeter and measure across C1. What's the number you see? 1.5. If I move it across C2, what's the number I will read? It will give me still 1.5. If I measure across C3, what's the number I will get? It will still tell you 1.5. And the reason is all the capacitors are connected in parallel combination. So the potential drop across each capacitor is exactly 1.5. That's how I got this number. So what's the remarks here is the V1 is equal to V2 is equal to V3 because all the capacitors are connected in parallel combination. Okay. So now let's calculate C1, and this is from equation. Okay. This is from equation. So how do I get this number here? So let me make it a different color here. Okay. How do I get this number here? Q1, Q2, and Q3. So the way I got it here is, so you see this equation here, Q1 is C1 times V1. All you have to do is multiply C1 and V1. C1 is 3, V1 is 1.5, so multiply, you'll get 4.5. Now next, C2 and V2, multiply these two numbers, you'll get 1.5. Again, multiply C3 times V3, you'll get 1.5. And if I add all the numbers together, Q1 plus Q2 plus Q3, the total charge will be 7.5. And the one more thing here is Q1 is greater than Q2 because C1 is greater than C2 and all the capacitors are in parallel combination. So the learning outcome here is if the capacitors are connected in parallel, then the larger capacitor will always store more charge and more energy. Okay. All right, so this is 7.5, and you can verify the total charge. This is the total charge, 7.5, and you can verify here. You see that this is the total charge here, that is 7.5 times 10 to the negative 13, which makes perfect sense. Okay, so now once you do that, let's go to the other one, the energy storage. Now, the last thing we'll do is energy storage. So it's all the tables are exactly the same here from this table here, and we already have calculated the v1, v2 and v3. So here the v1, v2 and v3 we already have calculated. So now we'll use the formula to calculate the energy stored in capacitor 1. So u1, this means the energy stored in capacitor 1, u2 is energy stored in capacitor 2, and u3 is energy stored in capacitor 3. Okay, and the formula to calculate energy storage is u1 is equal to half c1 and v1 square. So you have to use this equation here, c1 and v1 square. So we have c1 here and v1 here. So if I square 1.5 squared times 3 divided by 2, the number I will get here is 3.375. And now exactly I have to do for the C2. So V2 squared would be 1.5 squared and divided by 2. So number I get here is 1.125, and exactly it will be 1.125, and the total energy will be equal to all the numbers added together. So if I add all the numbers together, the number I get here is 5.625. So that's the here. So this number here is adding all the numbers here together. All right. And then you can verify here 5.625, the total energy. So in order to calculate the total energy, you simply click the total stored energy, and that is 0.56, which makes perfectly sense. That's what the number we calculated here. This is from the simulation, from the formula. And then the simulation just tells you whatever the number it tells you, just write down here 5.625, and then exactly, or if it is only saying you 5.6, you can simply write down 5.6 because you can only read 0.56 here. Okay, and exactly the same way you can fill all other tables here. So this is it, and answer all these questions here. So this is it for completing the parallel combination capacitor lab. If you have any other question, let me know. Thank you and have a wonderful time. Bye bye.